Our main goal today is to discuss something called the argument principle. So the starting point for talking about the argument principle is to think about the residue theorem again. So the residue theorem, one way to write it is 1 over 2 pi I times the integral of our function around a closed curve is equal to the sum of the residues of that function over the isolated singular points inside that closed curve. So implicit in this theorem is that the right-hand side is, in some sense, counting the singularities, right? That the singularities are being counted in some way on the right-hand side. You could sort of think about it as a weighted sum. That for each singularity, you're counting the residue at that singularity as sort of the weight at that singularity. But in particular, I mean, this sum of residues is registering each singularity, so it's in some sense being counted. And the goal here is that we're going to try to make this more explicit, that we can use the residue theorem to count singularities of functions, of analytic functions. And so why we would do this is that if we can count singularities, so I mean that might be interesting in its own right to count singularities, but another way you can use that is to count the zeros of an analytic function, because if f of z is equal to 0, then 1 over f of z is going to be a pole, right? So if you can count that pole, then you could count that 0, right? So you can count the pole of 1 over f, you can count the 0 of f. And if you can count zeros of functions, then you can count solutions to equations, right? Because if you're trying to find the solutions to f of z equals some fixed w, then you just look at the function g of z is f of z minus that constant w, and set that equal to 0. So the zeros of that function g would be the solutions of your original equation. Okay, so in particular, this idea that we're pursuing could be useful in saying something about the number of solutions of equations. So the remarkable thing is that there's a uniform expression that we can use to compute numerical information about the zeros and poles of an analytic function. And here's how you do that. It's rather surprising, but it follows directly from some rather simple considerations. So suppose we're looking at a 0 of an analytic function, and let's say that that 0 has order n. So we'll look at f. So near that 0, we can pull out a factor. Just thinking about the power series, right? So we've seen this before. You can pull out a factor of n, and g here, so g at z naught is not equal to 0. And what we're interested in, so what I'm interested in here, the numerical information about the 0 that I'm interested in is this n. And so basically I want to isolate that n. And here's how you can do that. So one thing you can do, you'll get that n to hop down there if you take the derivative. So let's take the derivative of f, and what we find is n times z minus z naught to the n minus 1 times g of z plus z minus z naught to the n times g prime of z. Now what I'm going to do in the second line is notice that these first two parts of this first term here are very close to f itself, right? And also this z minus z naught to the n has a lot in common with f. So if I write this in terms of my original function f, what I find is that I have n over z minus z naught times f of z plus, let's see, I have f of z times g prime of z over g of z. Right? So this is f of z times n over z minus z naught plus g prime of z over g of z. And so altogether, f prime of z over f of z is n over z minus z naught plus g prime of z over g of z. And what I can notice from this expression, or what should look kind of familiar, is that this n that I'm so interested in, that this looks like it should be the residue of this function, right? Because it's this coefficient of 1 over z minus z naught. And now just to confirm that, what we have to look at is this other part here, right? Notice that this function here, this is analytic. So this is analytic near z naught, and that's just because g at z naught is not equal to 0, right? So so we have this analytic function which is non-zero that we're dividing by. So we're just dividing two functions that are analytic near z naught, and so that result is analytic. So this, if we were to do a power series expansion around z naught, this would have a normal power series, not a Laurent series. So this really is so there's no other negative terms with a z minus z naught to the minus 1. So n really is the residue of f prime over f. So what we find is that n is equal to the residue of f prime of z over f of z at z naught. And now similarly, if z naught is a pole, and so remember that was in the case where our z naught was a 0 of order n z naught was a 0 of order n of f. So if we look at the case of a pole, so we get something sort of similar, right? F of z equals k of z over z minus z naught to the m, right? Where k at z naught is not equal to not equal to 0. It's not equal to 0. And so f is z minus z naught to the minus m times k of z, right? And then that's rather similar to our starting point up here. Right, z minus z naught to a power times an analytic function. Now we have z minus z naught to the minus m times an analytic function. And so it's not that hard for you to believe that if you do the same analogous computation, what you find is that the residue of f prime of z over f of z at z naught is equal to this negative m. Okay, so what we've found is that you can compute the order of a 0 of a function, f, and you can compute the order of a pole of an analytic function just as a residue of the same function, f prime over f. Right, so if you want to know something about the order of zeros and poles of f, you look at the residue of f prime over f around that 0 and pole. So now what we do is plug this information into the residue theorem, right? We just learned something about the residue of the function f prime over f and its connection to the order of zeros and poles of the function f itself. So we plug into the residue theorem, and so what we find is the situation here. So we suppose that our function f is analytic in some domain except for a finite number of poles, which we label with the letter w. And we have a typical curve in this domain, the smaller domain d prime, excluding the poles. And the interior of that curve, omega, is contained in the domain d. So, and also we assume that f is not 0 along gamma because we're going to be looking at f prime over f, so we want that that division to not be 0 where we're integrating. And then we also let z1 through zk be the zeros of f in the interior of gamma. Then letting n sub j denote the order of the z, the zeros z, and m sub j denote the order of the poles w. Then we find that 1 over 2 pi I times the integral of f prime over f around gamma is equal to the sum of the n's minus the sum of the m's. And this is just the residue theorem applied to f prime over f. So the integral around this curve of f prime over f is just going to be divided by 2 pi I is just going to be the sum of the residues at the singularities of f prime over f. But the singularities of f prime over f can only come from points where f is not defined, which would just be the singularities of f. So we just have the poles of f here, and it would also come from the zeros of f, right? So if we were dividing by 0, and we saw what happens when you have either of those situations above, that the residue then at those places is given by, in the case of the zeros, it's given by the n's, and in the case of the poles, it's given by the m's, right? So then we just have the negative m's. So then we just have the sum of the n's and the negative m's, and that's the theorem. So now to make this useful, what we have to do is understand better this integral here, because doing this integral might be rather difficult. And so you turn a problem of trying to count the zeros, some information about the zeros and the poles of a function, into computing this integral, which might be rather difficult. So we'd like to study this quantity a bit further. So first we need to take a look at the integrand because that is going to be important. Okay, so we're going to talk about f prime of z over f of z. So f prime of z over f of z, this might look somewhat familiar from calculus. First of all, the sort of intuitive way to think about it, at least from the Calc 1 perspective, is that it's the rate of change divided by the value of the function. In other words, it's the relative rate of change. So this is the relative rate of change of f. Okay, so it's the rate of change of f relative to the size of f. So already it has a pretty good intuitive meaning to it. You can see why it might be important. And the main thing to notice about this is that formally f prime of z over f of z, you might recognize this from calculus as the derivative of log of f. And so formally speaking, just applying the chain rule, log of f prime should be f prime over f. But unfortunately, so we need to be careful. Be careful because we need to make sense of the log. And so we have branches here. Our log isn't the nice simple function that we knew and loved in calculus. So so here, like, to make sense of log of f of z, you have to make sure that the image of f of z doesn't cross any branch cut you make in the definition of your log. So that could be a problem. But we can largely sidestep the issue by doing things the following way. So suppose f of z does not equal 0 on a simply connected a simply connected domain D. Then what we can do is let h of z be the integral from z naught, some fixed z naught in D to z. And so basically take any piecewise smooth path from z naught to z and integrate along that path the function f prime of zeta over f of zeta d zeta. And we know from previous work that this is an antiderivative of the function being integrated. So this function is well defined and satisfies h prime of z equals f prime of z over f of z. Right. So looking at this up here, right? So this log of f of z, which we kind of want to define, its derivative would have the property that it's f prime over f, right? But here we have constructed this function h, whose derivative is f prime over f. So in some sense, this h is sort of satisfying the need that we have for a function like log, or excuse me, log of f, the composition log of f. And what we can do here is to measure how far off h of z is from being a logarithm, from being the log of f. Right? Any log of f would have the property that its exponential was equal to f. Right? So we would want to see that the exponential of this function h was equal to f. Right? So basically we're looking at e to the h of z versus f of z. Right? So we'll look at the quotient of these two, f of z divided by e to the h of z. Right? So we know e to the h of z is positive, so we can divide by it. So what we can do is look at e to the minus h of z times f of z. And if we take the derivative of that, it's not hard to see that that's equal to 0, just using the product rule. So that this is going to be negative h prime, which is f prime of z over f of z times e to the minus h of z times f of z plus e to the minus h of z times f prime of z. And the f's cancel, and then that negative gives us a 0 there. So that means that f of z equals just some constant times e to the h of z. And what we can use is that the h of z naught is equal to 0. So this implies that f of z naught is equal to c. And now since c is not equal to 0, because our f isn't equal to 0, we can pick any number any complex number a that we want that exponentiates to c. Now there's not a unique one because the exponential is infinite to 1, but with that one particular choice, then our f is then e to the h of z plus a, right? Which we can just say that exponential, that h of z adjusted by that constant a, is g of z, right? Okay, so this g of z function, so we found g of z defined on all of D such that e to the g of z is equal to f of z. right? So just adjusting this integral here by an appropriate constant, we can obtain a function which exponentiates to f of z. So in a sense, this g of z is a logarithm of f of z. Okay, and so we're going to do an example to make sure that this is clear, because there's a bit of a subtlety here. So there's an important subtlety. In general, this g of z is not equal to some branch of the logarithm composed with f of z. Okay, so i.e. this g is not a composition. It's not a composition of f with a branch of log. Okay, and we'll see that in this example coming up here. So here's an example. So let's consider f of z to be z squared. And let's first, to make sense of things, we'll just talk about, we'll look at the principal branch of log of z squared. So if we look at capital log of z squared, this makes sense So that makes sense when z squared, the argument of that log, is in the domain of that log. So that's c minus on the real axis from negative infinity to 0 inclusive. So what we don't want, we don't want z squared to be in this interval of negative real numbers. Right, so when does a complex number square into a negative real number? Well, when you have a purely imaginary real number, right? So i.e. You don't want z to be a purely imaginary real number. So that's I times a real number. Okay, so the domain as a function, log of z squared has c minus the imaginary real numbers as a domain. Okay, so our log of z squared, if we remove the imaginary axis, right, then it's defined on the left and the right there. But we see that if we want to define log of z squared on a domain in the sense of domain like we've been talking about all semester, a connected topological, or a connected open set, then this domain of log of z squared as a function is not a domain, right? It's not connected because it has these two disconnected halves. And so if we want to talk about this log of z squared being defined on a domain, then we have to pick either right or left here. Okay, and that's a bit of an undesirable situation. However, so whatever the g of z function, so the g of z that's associated to this f of z from before, what we said is that what we concluded is that we could define that on any simply connected subset of the domain. Actually, to be more precise, it's any simply connected subset of the domain where the function is not equal to 0. So our function is not equal to 0 away from 0, but that's not simply connected. So in order to get a simply connected set, we would have to do something like maybe remove the negative imaginary numbers. Right? So this So if this is 0, we could take as domain everything, right, not cross the negative imaginary numbers, but we're allowed to cross the positive imaginary numbers, and our G would be defined on all of that. And so that's a bigger subset than just doing the composition log of z squared, right? So these are definitely, well, looking like different things here. The straight up composition of log with z squared and whatever this function g of z is. Now, it's instructive to get a sense of what's going on here, the difference between these two functions, the composition of log with z squared and this function g that we're claiming exists. So we'll be able to say more about that. And to get a sense of what's going on, so I've indicated the domain of f here, right? So the imaginary axis removed. And to get a sense of this f, or of log of, log of f. Imagine we walk around the unit circle in the right half plane here, so in this part of the domain of our function, and let's apply the function f. Well, this f is just z squared, right? So what that does is, so z squared takes the imaginary axis to the negative real numbers, right? So let me indicate that here. Right, so each of these dotted lines in the left picture here have ended up there, right? So remember what the squaring function is doing is it's not only stretching things out by a square factor, it's rotating things, and it's doubling the angle of rotation, right? So what's happening is that as you go from here to here, that the image of that is going from here around like this, right? So the angle gets doubled, like this dotted line down here moves that way, and this one moves that way, right? So that the right half plane gets folded around onto basically the whole plane, minus the negative real numbers. And here's the imaginary axis. Okay, and then log of z, so if you follow that up with log, so you do log of f of z, then that's just the unit circle, and log takes the unit circle to just the imaginary axis. So our principal branch of log, so this is negative I pi, and this is I pi. And if this is the y-axis, maybe I should have done these curves in a different color. So let's say this is red here, and then the image there is red by f, and then log of f of z is then just going to be this segment there. Okay, so that's log of f of z, what it does to that half circle. And if we look at the other half of that circle on the other side, then what that does is, well, again, that basically just continues around the circle one more time again. So if you think about this angle doubling in the left half plane, so things between an angle of pi over 2 and pi is now going to be between pi and 2 pi. So that's going to be in the lower half plane. And then things between an angle of pi and 3 pi over 2 is now going to be between 2 pi and 3 pi. So that's going to be in the upper half plane. So that what you do is, what happens is that this curve, so I'll try to keep it as close as possible. It's really going over the exact same curve again in the exact same direction. So it's doubling over that curve, and so then if you apply log, it's just going to double over this same curve here. And so again, it just retraces that curve. And so you see here, there's no way that we could continuously, so if I look back at this picture here, there's no way we can continuously bridge this gap between these two halves continuously and define this composition, right? Because when you go around this full curve here, this full unit circle, you're moving in a continuous curve, but the image log of f of z here, that it takes those two halves of that continuous circle and it breaks them, right? So when you're going along the red half, you go up to I pi, but then you discontinuously end up back down at negative I pi when you start the blue half, right? So it sort of breaks that circle. It has to break it sort of violently in half and then fit those halves separately on the same bit of the imaginary axis in the image. Okay, so there's not really any way we can bridge these two halves by filling in, some values along the imaginary axis in the domain there. There's just nothing we can do about it. But then what is the function g of z doing? So g of z is an analytic function, so it's continuous. So what is g of z deciding to do with this instead of what this composition is doing? So g of z, so let's say we have g of z defined, so the plane minus the negative imaginary numbers and 0, that's a simply connected set, so we should be able to define our g of z on that. And so what is g of z doing? Let's take the same starting point as we did with log of f and look at the unit circle here, the right half of the unit circle, and ask ourselves what is g of z doing to that? Well, so g prime and log of f prime, they're both equal to, right, so they both equal f prime over f, right? So they have the same derivative, right? So that means that log of f and g can only differ by a constant, right? So log of f minus g, the derivative is equal to 0 on the right half plane, right? So we're just looking at the right half plane where our log of f is defined, and that constant there. Well, if we exponentiate both sides, we get f is equal to e to the g times e to the c, and e to the g is just f. Right, so what we find is that our e to the c is equal to 1. So this constant must be some multiple of 2 pi I times k. Right, so log and f and g are, whatever this g is, are only going to differ by a multiple of 2 pi I times k. And in fact, this g is not unique. Nothing says that this g is unique, right, because it's just basically defined by this condition here. Right? So of course we can add 2 pi I times any integer to that and not change that. So we could just by adjusting our g by a constant, right? So if our g is not equal to log f on the right half plane, we'll just redefine g to be g plus whatever that constant c is, and then that'll still satisfy the condition that this function still exponentiates to f. So in any case, we can basically assume that our g in the right half plane is doing the same thing that f is doing. So that means that our g, right, that has to have the same image as log of f. Actually, I'm going to need to give myself a little more room here. Right, so if this is I pi and this is negative I pi and we have our imaginary axis and 0, the real axis running through here, then the image of that circle by our G, we can just assume that that's the same, or half circle is just that same strip that it was before for F. But what about the blue half of the circle? Well, that by the same argument, so now look at F, log of F on the left half plane, G and that log of F have to also just be differing by some constant, which is just an integer multiple of 2 pi I, right? So where log of F sent that half circle, which was here, right? So that blue strip there, where G sends the blue half of the circle has to just be that adjusted by a multiple of 2 pi I, right? So that would just take that blue strip there and just shift it up and down into adjacent horizontal strips, right? So it could move it up to to the strip that goes from I pi to I times 3 pi, or the strip that goes from I times 3 pi to I times 5 pi. But what it actually has to do is move it right up into the next strip, right? The strip that goes from I pi to 3 I pi. And the reason for that is just continuity. This function G is continuous, right? So where G sends this point that's in the middle, right there, between those two halves, the image of that yellow point has to be at the end of the red segment and the beginning of the blue segment, right? It can't be that so you can't have the blue segment like starting up here, right? Because then that breaks the continuity. So that circle going around there has to be brought to one continuous segment, otherwise you have a discontinuous jump. Okay, so that's what the function G is doing there. Or well, that gives you some idea of what the function G is doing and how it differs from just the ordinary composition. And so this G is definitely a distinct function from log of F. And in fact, we can compute explicitly. So this G here that we've illustrated sends the point 1 to the point 0. So what we can do is, using the definition that we established above, G of Z, if we want 1 to go to 0, we'll start our integration with 1 and integrate to Z. Our function F is Z squared, so look at zeta squared. The derivative of that is 2 zeta, and I have to integrate that d zeta. And that is the integral from 1 to z of 2 over zeta d zeta, right? And that so that integration is taking place in this domain, in this picture up here, right? So what we can say is that this is 2 times the log of z, where this log is the branch that's indicated in this picture up here. So we can say our log of z here is defined by the conditions that theta is between, let's look at the picture, it looks like negative pi over 2 and 3 pi over 2. And then that makes perfect sense with the mapping G that we see here, because then 2 times those theta values, right? If you do log of z, so you let z be on the unit circle there, then the length is 1, so the ln of 1 is 0, so you get 0 real part, and then I times theta, so your theta lies in this range, and then times I, so that'll be on the imaginary axis, and then times 2, so you multiply these thetas by 2, and you exactly get this range of thetas here. Right, so we see explicitly that our function g of z is 2 times this particular branch of the log. right? Which seems relatively close to, at least in some formal sense, the principal branch of log of z squared. In fact, this function here is equal to, so this branch of log is equal to the principal branch of log. Sorry, I don't know what I'm writing here. So this is this branch of log is equal to the principal branch of log if theta is between negative pi over 2 and pi, right? Because our so this branch of log here is defined in this range, whereas our principal branch of log is defined from negative pi to pi. So so they're going to be equal in the overlap of those ranges. Right, and so this seems related to log of z squared, but you have to remember that the log rules that you learned in pre-calculus don't really necessarily hold with log in complex analysis because of the branching problems. You have to they sort of hold up to multiples of 2 pi I. So we actually see explicitly from the work we've done here that generally log of z squared is not equal to 2 times log of z. Right, because log of z squared, if you look in the left half plane, like up in this region here, our log of z squared, that's different from our g of z function, but we know our g of z function is equal to that in the second quadrant there. Okay, so those functions aren't generally equal. So it basically turned out that in this case, all you had to do was, instead of look at log of z squared, sort of look at what an equivalent expression, or a sort of similar related expression, and then at least in some range that would define a suitable function g for you to use. Okay, so the basic intuition here for these for this function g, so when you have a function f defined on a simply connected domain, it's possible, like in this case with f, right? So look at this picture of what f does. As you go around the unit circle counterclockwise, f, the image, wraps that going once around, it wraps it twice around, right? So what f can do is wrap parts of your simply connected domain around the origin, so that it crosses a branch cut multiple times. Right? So if you were to try to just do log of f, then you would run into trouble with continuity, because as you go across the branch cut, log wants to take you from the top of this horizontal strip here, where the output of log is, and then instantaneously bring you back down to the bottom. Right? So that severs the continuity. So what this g does rather sensibly is says, well, instead of doing that jump, why don't you just continue on up into the next strip, right? And so that's exactly what's done down here with g. It says once you get to the top of this red segment, to the top of that horizontal strip, just continue on into the next strip. So trying to apply log gives you a discontinuity by bringing you back down to the bottom of the strip, but this function g rather sensibly just says continue on through into the next one. Okay, so this integration procedure gives you a uniform way of doing that. Okay, so much for the integrand f prime over f. So remember, what we were really interested in was the integral of f prime over f as we go around a typical curve along which f is not 0. So basically what I want to do is say that the integral along gamma of f prime of z over f of z, I want to say that f prime of z over f of z, that is that is g prime, where g is one of those logarithm-like functions of f, right? But in order to do that, we need to have, so this is only valid, right? So this is only going to be valid, only valid in a simply connected domain where f is not 0. Okay, and so like in this picture on the left with gamma, like there might be poles and zeros of f inside of gamma, so we can't just like consider the whole region, the whole simply connected region. You can't just like take a big disk or something to put gamma in that's simply connected, because we have to also consider the f not be equal to 0. So basically what we do is something like the following. So to ensure that f is not 0, well, we know that f is not 0 along the curve gamma, right? So I claim that as long as, and I won't support this claim, I'll just, it seems plausible, as long as you stay close enough to the curve gamma, your function f is going to continue to be not 0, right? So this is basically by continuity, as long as you stay close to the curve. So I've sort of outlined the region. So sort of to the right of the curve, as you go around counterclockwise, you have this blue barrier, and the left you have this green barrier. So as long as you stay between those barriers in the region that's hashed out in yellow there, your function f will remain non-zero. Okay, so you just sort of stay close to your curve and consider that to be basically your domain. However, I mean, it's clear that if you do this around the entire curve, this is not simply connected, right? Because you have, because, I mean, particularly the curve gamma itself, then, surrounds a bunch of stuff that's not in the yellow region, right? It's a closed curve in the yellow region, which doesn't contain stuff in the yellow region. So what you have to do is, I've indicated in red, you basically cut off this region, right? So you sort of exclude a point from gamma, and then you exclude all of the stuff in that yellow region across that segment, and then the claim is that set then is going to be simply connected. Again, a bit of an unsupported claim, but seems intuitive enough. So if you draw any closed loop in that skinny region there, it's always going to contain the stuff inside of it, right? So you can no longer use the full loop gamma because you've cut off that one point there. Okay, so basically in this simply connected yellow region where your function is not equal to 0, now we're going to have an antiderivative for f prime over f. You're going to have this function g, sort of which serves as a kind of a logarithm of f. So let's fix up our computation. So this part over here, the simply connected domain where f is not equal to 0, that's that region that's hashed in yellow on the left. So that'll be okay. But g really isn't defined along all of gamma because we excluded that point from gamma. So let's say, so in here on gamma, there's a point, I don't know, let's just say p that we're excluding from gamma. So we really have to exclude that point p. So we'll just, well, you can remove a single point without changing an integral, right? Because the point has sort of area content 0, or length. It has length 0, so that's not going to affect this line integral. So then I can say that is equal to, so let me just delete that equal sign, and so that's going to be equal to gamma minus p. Okay, and then that is going to be equal to, okay, we need a little bit more setup here. So gamma minus p, let's say that curve So that curve, let's say that it's on the open interval. So let's say we parameterize it on the open interval from A to B into C, right? So this point P here, it's the limit as T goes to A from the right of gamma of T, all right? And it's also the limit as T goes to B from the left of gamma of T, right? Okay, so our integral here, continuing this integral computation, that's equal to the integral from A to B of, well, we have parameterizing a G prime at gamma of T, and then dz is gamma prime of T dt, right? And that is equal to the integral from A to B of G of gamma of T, just by the chain rule, prime dt. And so what this is, well, our G is not defined at gamma of A or gamma of B, right? So this is the limit as T goes to B from the left of G of gamma of T, and minus the limit as T goes to A from the right of G of gamma of T. All right, so we can't actually pull those limits in through G because G is not defined at the point P. So to get a sense of how to evaluate this integral with those limits of G, let's imagine what's going on. So our function gamma, or sorry, our curve gamma, we have this closed curve, and let's apply the function f. So when we apply the function f, f of gamma is going to also be some closed curve, and so I'm carrying this picture up here. I'm carrying that down here with f, and so that point P there, maybe that goes down here, as you see in the picture where I've indicated f of P there. And so as that curve goes around, just like in the case with z squared that we looked at above, right? When you look at a closed curve, it could possibly loop around more times than it looped around in the domain. Right? So we're just going once around this curve gamma in the domain, but in the image, right? So here we see kind of three different loop-de-loops that are happening in our curve. Right? So I'll give you a second to kind of stare at that. Follow the red arrows around, starting from f of P. Right, so our function f could be doing something like that, and so what is our function g doing, right, which is, remember, a kind of logarithm of f? Well, g, so it's going to send f of p somewhere, or so it's going to send, well, not really p, because remember, g isn't defined at p, but sort of points nearby P. So as you start going around gamma, so basically points near gamma of A. Right, so gamma of A goes to P for values of T just slightly bigger than A. So gamma is gonna, or G is gonna send them somewhere. So you see in this picture, that's sort of down here in this picture, and those have to be such that when you apply the exponential function, right, that you end up at f, because this function g has the property that that e to the g is equal to f. And so in this picture for g, I've marked the horizontal strips corresponding to like the principal branch of the logarithm. So every time in our picture with f, what f does to the curve, right? Every time you pass a branch cut of the natural logarithm, you go through one of these dotted lines in the picture g. And so you're following this curve f around. When you go through the negative imaginary axis, you can imagine that's when you're passing through a dotted line here. Right, so as this loops around, every time you pass through a branch cut going around counterclockwise, you go through one of these dotted lines that indicates you've gone into a new horizontal strip in this picture here. So looking at these limits that we want to compute here, in the picture, I'm really out of colors here, oh well. So in the picture, the limit is t goes to b from below of g of gamma. That's like this point up at the top here, right? So your black curve, that's the g of gamma. And as t goes to a from the right of g of gamma, that's like the bottom point here, right? And the difference between those 2 points, well, you can see that basically, since those points, when you exponentiate them, right, they're corresponding to this beginning point of the curve f of gamma, which is this f of p here. And so this top point and this bottom point of the g of gamma curve, they're both going to the same point down here, f of p, under the exponential. And what that means is that they must just be separated by a vertical distance of 2 pi times some integer, right? So we just look at this vertical distance here, and that's got to be 2 pi. So that's got to be 2 pi times some, well, I guess 2 pi I times some L, where L is an integer. And what that L is, so each one of these, right, so each one of these strips is a distance of 2 pi, is a width of 2 pi. So all this is here is the number of those strip lengths that you've covered from g of gamma as you go up. But starting at the bottom here, every strip length just corresponds to going around. So in the picture of f of gamma, and so we're starting here at f of p, that just corresponds to going around another 2 pi around the origin by another 2 pi, right? So every strip length in this picture here just corresponds to going around the curve f of gamma by another 2 pi. So in other words, this L here is just the number of times that f of gamma has gone around the origin. So this integral, so we started with this integral up here, and what we've wound up at is that this is 2 pi I times the number of times f composed with gamma winds around 0. And so if we compare that to, right, so remember that, so if you divide this 2 pi I on the other side of this, remember that we decided before that our zero pole count theorem told us that this integral divided by 2 pi I was equal to the difference between the number of zeros counted with their orders and the number of poles, minus the number of poles counted with their orders. So what we find is what's called the argument principle. So the argument principle is that with the same hypotheses as in the zero pole count theorem, that the sum of the orders of the zeros minus the sum of the orders of the poles of your function f, that is equal to the number of times f composed with gamma, so f applied to gamma, that closed curve, how many times that winds around 0. And the number of times that winds around 0, another way to say that is that it's the total change in the argument as z traverses f of f composed with gamma. So the total change in the argument is just 2 pi times the number of times you wind around, right? So if you take that total change and divide by 1 over 2 pi, that again is just the number of times f composed with gamma winds around 0. So that's why it's called the argument principle. So it's the total change in the argument of f of that curve gamma, f applied to that curve gamma, that counts the number of zeros and poles, this difference. So intuitively, I kind of like to think about this theorem like this. So like a zero, near a zero of order n of your function is like basically a constant times times z minus, and let's just say we're centered at 0, or you recenter so that whatever 0 you're looking at is the center of things. So your function of order 0 of order n is basically like z to the n times a constant, right? So it's sort of proportional to z to the n. And z to the n, like what z to the n does, if you think about the like the unit circle, z to the n takes that unit circle and it wraps it around itself n times, right? So like z squared wraps around 2 times, and z cubed, and so each third of this circle, each third of this circle gets mapped onto the full circle by z cubed. And similarly for z to the n, each nth of the circle gets mapped onto the full circle. So a zero, so like near a 0 of order n, your function kind of has this like circulating behavior that is like circulating by a power of like n times around that 0. Whereas if you have a pole of order m, then your function is sort of proportional to 1 over z to the m, right? So which is z to the m inverse, right? So it's z to the m to the minus 1. And on the unit circle, you do the z to the m, that's wrapping things around m times, and then that inverse is on the unit circle is the same as a complex conjugation. So it's a flip. So that sort of, it flips the circle upside down. So instead of like where we were going around like this, now it's going around in the opposite direction, right? So whereas in the case of a 0, you're going around in the counterclockwise direction. In the case of a pole, now you're going in the clockwise direction. So that's so basically the argument principle says that this curve, which encloses all of these zeros and poles, that sort of all of those little circulations that are being caused by the zeros and poles, they all add up. So literally they're additive. Like you add up all of the the positive contributions from the zeros and then the negative contributions going around in the other direction from the poles, and that's what you get is the total change you get the number of times that the curve, when you apply the function, winds around 0. So it's so in some sense it makes some kind of, there's some like weird logic to this argument principle, weird intuitive logic to it. Okay, so the last thing we'll do is look at an example, the last thing we have time for. So we'll find out how many zeros f of z equals z cubed minus 2z squared plus 4 has in the first quadrant. Okay, so what we'll do is so basically to find how many zeros we have in the first quadrant, well, we're gonna attempt to use the argument principle. So we need to circle our zeros in the first quadrant with a curve. And so what's going to work is that we'll take a curve like this. So that's the real axis, imaginary axis. Then our curve, like this, is going to be r, and this is going to be I times r. And our curve will go around a wedge like this, right? So this is an arc of a circle here. And if we make r large, so we'll just assume r is very large. And we know this is a polynomial, so it only will have finitely many zeros. So if r is large enough, we're eventually going to get whatever zeros might happen to be in the first quadrant. And what we need to do is, so we need to look at, so we call this gamma, say, sub r. Then we need to look at, f composed with gamma, right? Okay, so let's look at them along each of these segments. So along 0, r on the real axis, at our variable, we can just take our variable as x. So we have x cubed minus 2x squared plus 4. And it's a trivial matter using calculus to prove that this is always greater than 2 on this interval. So if I indicate this path in red here, well, of course the image is real, so the image is just going to be on the imaginary, or on the real axis as well. And let's see, at 0, this thing is 4. So let's say this is 2, and this is 4. Then our thing, it starts at 4. It immediately starts to get smaller because when x is small, that squared part is bigger than the cubed part. So it gets a bit smaller, but it never goes less than 2. So it heads that way for a little bit, but then once r is big, of course, this is going to infinity, right? So this is going to go out this way, right? So when r is big, this is going to go way out this direction. Okay, so that's what's going on there. The next thing that's easiest is the I times 0r, right, on the imaginary axis. So there our variable is y, and we have negative iy cubed plus 2y squared plus 4, right? And so this is 4 plus 2y squared plus I times negative y cubed, right? So of course this thing is always negative in the imaginary direction, and it's always greater than or equal to 4 in the real direction. So this curve is always on the right hand side of that dividing line there. So that one, so if I indicate that in green going this way, so it has to meet up with the red curve at its starting point. So it's going to meet up like here, right? So it's sort of coming in that direction. And what do we see here in this curve? So the x component is like quadratic, and this is cubic. So the relation between the second component and this first one is that it's like the second's like a 3/2 power of that, right? So it's like, and there's a negative. So it's like you're seeing negative, sort of like the graph of negative y equals negative x to the 3/2 power, something like that. So your graph, so roughly speaking, it would, sort of be like this. Yeah, so it's going to be coming in kind of like that. Okay. And then we have to worry about, so the one to worry about is that middle leg there connecting the two in blue. And so for that, so that along there, our blue, that's r e to the I t, right? So we have r cubed e to the I 3t minus 2r squared e to the I 2t, and then plus 4. And the basic point of this is going to be that this thing here, this is much bigger than the rest of this. Right, so what you can do is you can choose r so large that r cubed e to the I 3t, that the length of that is bigger than the length of 2r squared e to the I 2t minus 4. Right, so if this first part, if when you subtract from this first part, this second part, if this has bigger length than this, then this quantity can never hit 0, right? So it's always so it's never gonna hit the origin. So basically, what you can imagine is like this one here, which is so much bigger. That part, that's just a simple, like as t goes from 0 to pi over 2, e to the I 3t goes from 0 to 3 pi over 2, right? So that one in yellow, like it's going to pick up from the end of this red, roughly speaking, and sort of just go around from 0 to 3 pi over 2, right? In just some gigantic arc like this. And the rest of the stuff here, right. So anyway, the rest of this stuff, so let's say this thing, that's just stuff that's being added on to that yellow. Let me clean this up a bit. So that's just stuff that's being added on to the yellow. So you can imagine, as this, so the yellow is going around. The true quantity that we want is that yellow plus a small little annoying perturbation, right? So like you have like small little perturbations as you go along the yellow, right? But those perturbations, they never come out far enough to touch 0, right? So they don't get to 0. So if you follow the true path around, so that's in blue, right? So it's kind of following these black arrows here, right? You would still find that the way they wrap around. So I guess, so eventually the, so when the yellow ends, I guess that has to, the plus the black has to connect up with the green. So this must be sort of like that. That must have just wound around the origin one time, right? So basically you had this like, this, you can think about it as like, think about it this way, like the yellow going around there. So like the origin is the sun, okay? The origin is the sun. The yellow, that's just the that's like the Earth going around the sun, going around the sun during the course of the year, and the blue is just like the moon orbiting around the Earth, right? So how many times does the moon go around the sun in a year? Well, it goes around one time, right? Because we know the Earth goes around one time, and the moon has a relatively small orbit compared to the distance from the Earth to the sun, right? So even though the moon has a sort of more complicated trajectory around the sun because it's also simultaneously moving around the Earth, we can still confidently say that the moon only goes around the Earth, around the sun once in the course of the year, right? Because it has again, relatively small, it's at a relatively small distance from the Earth with respect to the distance from the Earth to the sun. Okay, so these little perturbations on this on that yellow curve aren't enough to move around the origin, so that's not going to affect the number of times the full curve has gone around the origin. All right, so all in total, you follow the red and then the blue. Oh yeah, I didn't do a great job here, so there should be like, I guess something like that. Yeah, so the red and then the blue and then the green, you see that the origin is encompassed one time, right? So we see that our total change, so 1 over 2 pi times the total change in arg, that's just equal to 1. Right, and our function doesn't have any poles, so this just must be the sum of the orders of the zeros, and so that must mean that there's a single zero of order 1. Right, so this implies that there's a single zero of order 1. Okay, so this polynomial must have a root somewhere in the first quadrant, and it's not a repeated root. Okay, that is all we have time for.